Hi, everyone, and thanks for joining us for today's webinar. As you may know, Interface Fluidics hosts webinars every month or so covering different technologies and research for oil and gas. Today's topic is hydraulic fracturing optimized, preventing chemical incompatibilities. Our speaker today is Jolene Fortin, Technical Account Manager. Her background is in chemical technology with previous work in core flooding laboratories and several years of experience in the Interface lab. Take it away, Jolene.
Great. Thank you so much for the introduction, Lee. So today I'm going to talk about Interface's approach to preventing chemical incompatibilities, as well as walk you through a few different case study examples, including surfactant selection for the Eagleford, a client who experienced a few wax damage challenges, as well as some of our work with rock water on regained conductivity. So at Interface, we help you screen through the right chemicals for your well under reservoir relevant temperatures and pressures. Our visualization capabilities allow us to identify potentially damaging effects like emulsions, solids precipitation, destabilization of HVFRs and other chemistries at high temperatures, as well as chemical incompatibilities and more. The first thing that I'd like to talk to you about today is Interface's fracturing fluid optimization solution. And I'll walk you through the technology just a little bit before we jump into some of our real world examples. So at Interface, we create your reservoir on a microfluidic device by taking your permeability, porosity, pore throat size distribution, as well as morphology and wettability characteristics, and creating a representative reservoir analog. Here you can see one of our flowback analogs, which represents the region where the frac meets the matrix. On the right-hand side, you can see an SEM image of our flowback analog, where we have a dual permeability, dual porosity device with a frac region that represents about a 40-70 mesh frac sand and a nano permeability matrix. This device allows us to perform representative fluid screening at reservoir temperatures, pressures, and confinement. We take your reservoir fluids, your oil and water, bring everything up to relevant temperatures and pressures, and we're able to provide you with an excellent platform to screen through your chemical package. So now I'll show you a little bit about what this process actually looks like in action. Here we have a video of our device under fluorescence microscopy. The first step is to saturate the analog with your reservoir fluids. We also tune the wettability of the device to be representative of your initial starting conditions as well. So the substrate that we're using here is silicon, which is inherently water wet. If you're interested in maybe looking at carbonates, or you're interested in how a certain chemistry performs in an intermediate or oil wet situation, we're able to tune the wettability to accommodate that. We then inject your base frac fluid and additives of interest across the chip from left to right. The analog then undergoes a 2-hour soaking period before we flow clean oil back across the system. We're able to visualize everything optically throughout the entirety of the process. The primary performance metric that we use to differentiate product performance is the volume of oil flow back. And we actually measure this on our device in accumulation channels, which you can see in the picture there. We also look at displacement efficiency, and this is an indication of how well an additive works at displacing the oil during the injection phase. You can think of this a bit like your stimulated rock volume. We also look at regained saturation, and this provides us with an indication of any damage that may be occurring in the system, preventing oil from resaturating pores and flowing back. We also look at wettability modification, and we measure contact angle in situ optically before, during, and after chemical injection. So direct pore scale imaging is one of the most powerful tools that we've brought at Interface to the oil field laboratory. Measurements like flow rates, pressure differentials, and effluent analysis are all indirect measurements of what is happening inside the porous media. Through direct imaging, we capture interactions in real time, and we open up new avenues of analysis and increase accuracy while still retaining the quantitative information that is offered by traditional analysis. So one of the unique abilities is to actually see the pore scale phenomenon. And we do this through a few different techniques. The first one that we use is fluorescence microscopy. So oil naturally fluoresces, and we can capture exactly where in the device the oil is, as well as look at different things like oil droplet size and fragmentation. We use bright field to capture any precipitation, asphaltene, or solid deposition that we may be seeing throughout the process, as well as cross-polar microscopy. So cross-polar is a standard method for looking at waxes, and we can essentially add that on to any of our different techniques to identify if you're having wax formation or other crystals forming throughout the process. So here's an example of what we see at the pore scale, and this is in one of our flowback devices. So on the left-hand side, we have a control case where we flowed brine through the system. You can see in both the fluorescence and the bright field microscopy images that it's very clean. We don't see any debris or emulsions forming. On the other hand, in the right-hand side, this is after a specific chemical additive has been flown through the system. And you can see both in the fluorescence and bright field cases that there is emulsion formation. And that's captured in the bright field imaging throughout the dark regions. So we're actually able to even look at that emulsion distribution and quantify what's happening in the porous media. All right, so now I'll jump into our first case study. Here we're looking at a frac additive selection as well as a study on temperature dependency. So essentially what we had was a United States-based operator who was seeking to identify the right surfactant products for their Eagleford reservoir. The conditions that they were working with were relatively high temperature, over 300 degrees Fahrenheit, as well as high pressure and very low confinement. So the data that they were given from the respective chemical vendors was typically done at ambient conditions or no greater than 200 degrees Fahrenheit. And this doesn't necessarily represent what was going to be happening in their reservoir. So what we're able to do at Interface is actually look at the chemical performance under reservoir relevant temperatures, pressures, and the nano confinement as well. So in this case, our client's goals were to screen through a few different surfactant products to identify the optimal product, as well as test the impact of temperature on their performance. So here you're looking at one of the sets of results from this case study. So with this case study, we looked at 6 different products and we tested them at 2 different loadings, 1 and 2 GPT. The analog that we designed for this client had low permeability with very small pore throat size. They were working with a high temperature reservoir of 300 degrees Fahrenheit, and the wettability was intermediate to oil wet. And here you're looking at the results from the 1 GPT study. So essentially what we see is that we've ran a control case, which is the black line sort of in the middle. And there were 2 products identified that outperformed the brine control. Both products A and B showed a considerable improvement over pure brine. On the other hand, products C, D, E, and F actually were shown to damage the reservoir and prevent oil from flowing back. And they resulted in significantly worse performance than just a brine case. So we also evaluated in this case study the impact of loadings. So here we're seeing on the left-hand side, this is the brine control during the oil flowback phase. So you can see that the oil is resaturating a lot of the pores as well as the frac region. Now on the right-hand side, you will see the 1 GPT case of this additive play. And you can see there's actually better oil flow back and better regained saturation than the brine control. However, when we double the concentration of this product, what we see is that there's actually a considerable amount of damage that occurs. So it prevents any of the oil from actually flowing back and the result is significantly worse than the brine control alone. So in some cases, it is very important to use higher concentrations, often in, for example, polymer EOR. A higher viscosity or a higher loading results in increased sweep and better oil recovery. But when we're looking at fracking, sometimes by increasing the concentration, we actually see reduced or hindered performance. So in this case, it was really less is more. And what we believe at Interface is it's not only important to identify the right product, but also look at the right or optimal concentration so that you have the right performance. So we took one of the products that performed very poorly. In this case, it was sample C, and we had done everything at 300 degrees Fahrenheit. And on that bottom video, you can see that there's very minimal oil flowed back and significant regions of the frac zone are blocked off. But when we lower the temperature to 160 degrees Fahrenheit, which is the top video, you can see that the performance significantly improves. So this was a case where the chemistry of interest was demonstrating considerable thermal degradation. So a chemistry that may perform well under ambient conditions or benchtop testing doesn't necessarily perform well at reservoir conditions. So it's very important to factor everything in. And what does that look like under bright field imaging? So essentially, when we see reduced volume of oil flowed back or poor performance in a product, often what we see is damage or blockage happening in the porous media. In this case, we saw different precipitation and deposition happening throughout the analog. We see it in the upstream accumulation channels. We see it in the frac zone. We also see it throughout the nanomatrix and downstream. All right, so now I'll talk about our wax deposition evaluation. So this project was designed to evaluate the impact of wax deposition on oil flowback. In the interface experiment, essentially what we did was we flowed oil at a certain temperature. We then cooled down the analog for 1 hour. We flowed oil again at a lower temperature. We heated up the analog back to the initial temperature for 1 hour, and we flowed oil again a third time. And what we saw was that during the cooling process, there was a considerable amount of wax deposition and wax formation. So by forming the wax, we had a severe impairment of the ability of the oil to flow across the device. When we raised the temperature back up, we saw oil begin to flow again as the wax deposition or as the wax redissolved into solution. But interestingly, despite raising the temperature up again, there was still an overall reduction in oil flow back by about 23%. And this is what that looks like when we actually image our device. So we have 3 different regions here that we're looking at. We're looking at the production channels, which are upstream, the frac zone, as well as the pore zone. And we evaluated these in each of the 3 stages. And what you can see is that in the first stage, we have no signs of wax, but when the temperature is lowered, we do see wax formation. Then again, when the temperature is raised, those wax deposits disappear, but there is still a reduction in oil flowed back. So what we found in this case was that although wax precipitation or deposition is considered to be a reversible process, it still causes a reduction in the oil flowed back when the temperature reaches the initial value. And on average, we saw about a 20 to 25% reduction in oil flow back. All right, so now I'll talk a little bit about our regain conductivity optimization. This is actually a product that we commercialized in partnership with Rockwater as well as Ovintiv. And essentially what we've done here is we've created a prop and pack on a chip. So we've replaced the traditional prop and pack with a highly repeatable porous media. The advantage there is that it's a controlled system, so it's very repeatable. It's significantly faster than traditional testing. We're able to do it at less than half the cost, and we require significantly less sample. When we talk about optimizing FRs, we're looking at selecting the right friction reducer for your application, identifying the right concentration, seeing whether you want to use powder or liquid depending on the performance and the cost, evaluating the breaker selection, breaker optimization, looking at brine compatibility, whether you're looking at using fresh water or recycled water, produced water. That's all something that we can evaluate, as well as looking at things like the impact of iron. So in this study with rock water, we evaluated 6 different friction reducers. And in this study, we looked at them with and without breaker. So in all cases, we found that the broken friction reducer resulted in less damage than unbroken friction reducer. We were also able to gain key insights like the solubility of the FRs, certain injectivity problems that may occur, as well as the long-term performance. We also were able to evaluate the differences in liquid versus powdered FRs. So what we found was that in general, the liquid FRs were more stable throughout the injection process, whereas powdered FRs had a bit more variability. We also saw, like for example, the purple powdered FR, FR9, it exhibited a higher tendency to have solubility challenges compared to liquid FRs. We also found that some of the liquid FRs, like FR5 and 6, required less breaker to achieve the same level of cleanup as some of the powdered FRs. So in this case, which is a completely different set of FRs, we took 2 FRs, FR A and B, and we evaluated them with and without breaker. As expected, the FR with breaker cleaned up significantly better. We then took that system and we replaced it with a high API brine. And what we found in this case was that both FRs that we looked at demonstrated a good salt tolerance. But essentially what we're demonstrating here is that we can work with a wide range of brine salinities above 200,000 TDS to really evaluate the impact of how your FRs may perform in a high saline environment. So now I want to talk to you a little bit about the gummy bear challenge, which was featured on the cover of JPT a while back. So looking at this gummy bear challenge, Interface is able to look at prevention and remediation of gummy bears or the mystery gunk that may be coming out of your well. Of course, it's preferable to prevent this from happening. And when we look at prevention, essentially we're looking at evaluating the compatibility of FRs and the additives with the brine chemistry, evaluating iron sensitivity, the actual selection of your friction reducers for the given case, and breaker concentration. So Stephen Rassenfoss, who is the author of the gummy bear article in JPT, he quoted a supplier who mentioned that low molecular weight FRs may be better at preventing gummy bears due to their ability to clean up better. The article also stated that steps should be taken to ensure that friction reducers break down after use, and that using certain polyacrylamides with low to moderate molecular weight clean up better than those with high molecular structures. The paper also stated that it's reasonable belief to high molecular weight polymers are more likely to interact with pyrite, but this is something that's still being investigated. So some of the experts who've looked at these gummy bear challenges, especially gummy bears that are blamed on friction reducers, have identified that typically in laboratory environments, these FRs are evaluated with tap water or unrealistic brine concentrations, and that essentially enables them to perform better in the laboratory than the field. So at Interface, we're ensuring that there are realistic conditions in the testing, including the brine composition and other variables that may impact performance. We are also looking into remediation with different chemical suppliers. So some studies have shown that there are positive results from pumping different chemical remediation treatments into damaged wells. In that interface, we can essentially generate these gummy bears in our device and then look at different chemical remediation treatments for cleaning them up. So essentially, we can screen through a wide range of different FRs, look at the right breakers and concentrations to ensure that you'll have cleanup in the reservoir, therefore preventing these situations from happening. And then if they do happen, we can help you out there as well. So in conclusion, our technology enables you to screen through a wide range of different chemistries at reservoir relevant conditions. We can visualize the damage occurring, including emulsions, precipitation, and more. Interface Fluidic makes extreme condition fluid analysis quick, accurate, and accessible to the energy industry for more accurate, cost-effective, and environmentally conscious decision-making in the field. So thank you.
Yes, thank you for that, Jelaine. We do have a few questions here in the chat. Are you limited to testing certain chemistries?
No, in general, we've tested a wide range of chemistries. We've looked at anything from nanofluids and surfactants, friction reducers, crosslinkers, HVFRs, and so on. The one area that we don't work on is drilling fluids or any fluid that has a high amount of solids. Just because of the confinement that we're working with, it's very difficult to repeatably pump any solids through our system.
Okay, and what is our maximum operating temperature and pressure?
So our maximum operating temperature is 400 degrees Fahrenheit. We can operate with pressures up to 15,000 PSI or 1,000 bar. Typically, when we're looking at fracturing fluid optimization, where our clients are sending us dead oil samples, we're typically somewhere in the 4,000 PSI range.
Okay. For the FR regained conductivity, what propant would be a close representation of our microfluidic device?
Great question. So the device that we have actually fabricated typically to use for regained conductivity was designed based off of a 4070 mesh propant. But because of the ability at Interface to customize different systems, we're actually able to match, 5070 mesh or 100 mesh propant, just depending on what you're looking for.
What are the lower limits on permeability and porosity for what we can fabricate for the matrix portion?
Yeah, so the lower limit on permeability is hundreds of nanodarcy, which correlates to about a 60 nanometer pore throat size. The porosity of the matrix, including the pores, is around 5%. So the pore throats themselves have a very, very low porosity, but we factor in the pores as well. And we don't have a defined upper limit.
Yeah. What kind of pump are we using for our 15,000 PSI pressure?
Yeah, so all of our pumps are specialized for microfluidics and working with very low flow rates and volumes. The high pressure 15,000 PSI pumps are supplied to us by a vendor called Satoni.
And what is your pore size range?
So our pore size goes as low as, our pore throat size goes down to about 60 nanometers. Our pores are typically in the range of 50 to 100 micron. But as I mentioned earlier, we really don't have much of an upper limit. We can go such that we have tens of Darcy permeability.
Okay, great. Thank you so much, Jelaine.
Great. Thank you, everyone.